In this presentation, we are going to examine reactions of monosaccharides. A monosaccharide is either an aldose or a ketose, which means that monosaccharide contains either an aldehyde or a keto group. Aldehydes could be oxidized to the corresponding carboxylic acids, which means that they would reduce an oxidizing agent. So such sugar would be called reducing sugar. As it happens, ketones under reaction conditions could be isomerized to aldehydes, and that means that in turn ketones or ketoses could also be reducing sugars. So let's examine that. One mild oxidizing agent or oxidizing reagent is Tollens reagent. A Tollens reagent is a basic solution of silver nitrate. It's actually silver 1 plus ion that is complexed with ammonia in solution of sodium hydroxide. It's very mild oxidizing agent, and it oxidizes aldehydes to the corresponding carboxylic acids. But it is so mild that leaves hydroxyl groups, alcohols, unaffected. And the reaction is shown here. So in the presence of Tollens reagent, monosaccharide aldose is oxidized to the corresponding carboxylic acid. Silver is, in the course of reaction, reduced, so silver 1 plus ion is reduced to metallic silver, and if reaction is done properly, silver mirror deposits. So that's positive Tollens test, deposition of a silver mirror. And in fact, that's how silver mirrors are prepared. Another related reaction is Fehling test. Fehling test is basic solution of copper sulfate. And the outcome is the same, in that aldose is oxidized to the corresponding carboxylic acid. In this case, positive reaction, positive Fehling test is formation of red copper 1 precipitate, copper 1 oxide. So copper is reduced from copper 2 plus to copper 1 plus. Now carbohydrates that give positive Tollens or Fehling tests are called reducing sugars, and those that do not are called non-reducing sugars. So at first glance it may appear that an aldose would give positive test and ketones negative, because ketones cannot be oxidized to carboxylic acids. But that's actually not the case. This solution is a basic solution. It's actually a strongly basic solution, and under basic conditions, a ketose can be isomerized to an aldose, and that's shown in an equation here, isomerization of fructose to glucose. And so, since both Tollens and Fehling reagents are basic, ketose under reaction conditions is going to isomerize to aldose, and then aldose in turn will be oxidized or give positive test. And therefore, ketose will also give positive test for reducing sugar. And so ketoses are reducing sugars. The only way to prevent such isomerization, or actually to prevent test from being positive, is to convert carbohydrate into a corresponding glucoside. That means, since most of the pentoses and hexoses are in cyclic form, in form of either hemiacetal or hemiketal in aqueous solution, so that means that they need to be converted to glucoside, so that hemiacetal or hemiketal is converted to acetal or ketal. That's what glucoside is. Acetal corresponding acetal or ketal. Hemiacetal or hemiketal can undergo reverse reaction to give an open chain aldehyde, which in turn can be oxidized. On the other hand, acetal or ketal cannot undergo ring opening reaction and give negative tests, so they are non-reducing sugars. So Tollens and Fehling tests distinguish hemiacetals from acetals and not aldose from ketones. And to state one more time purpose of these tests, Tollens and Fehling tests are used to distinguish hemiacetals or hemiketals from acetals or ketals. Acetals or ketals are also called glucosides, and they are not used to distinguish an aldose from a ketose. because they cannot distinguish an aldose from a ketose. So hemiacetals or hemiketals are reducing sugars and they give positive Tollens and Fehling tests. Acetals or ketals, glucosides, are non-reducing sugars and they give negative Tollens and Fehling tests. This brings us to glycosidation reaction for preparation of acetals or ketals from hemiacetals or hemiketals. So when a cyclic hemiacetal or hemiketal is formed by a monosaccharide, it can react with an alcohol. An alcohol could be a simple alcohol, as shown here, ethanol, or it could be more complex alcohol. For example, another monosaccharide is also an alcohol because it has numerous hydroxyl groups. So in a reaction with another alcohol, acetal or ketal is produced. And that acetal or ketal, in this case, is called glucoside. In general, in chemistry, when we convert hemiacetal to acetal, we call it acetal, or hemiketal, we convert it to ketal and call it ketal. In carbohydrate chemistry, we call it glucoside. So acetal or ketal in general are called glucosides. So when glucose reacts with ethanol, product is ethyl glucoside, corresponding ethyl glucoside. In this case, starting material was beta-D-glucose, so product is ethyl beta-D-glucoside. Now, a reaction of single anomer can lead to formation of both alpha and beta glucosides, and you may want to review anomeric effect to understand this. In this case, in the equation above, bond to the oxygen, newly formed bond to the, in this case, oxygen, is shown in red to emphasize glycosidic bond. On the previous page, glucosides were O-glucosides. O-glucoside means that bond to acetal or ketal carbon was formed by the oxygen. So those would be oxygen glucosides. If reaction is with nitrogen-containing compound, then products are corresponding N or nitrogen glucosides. So such a suitable compound is imidazole. So reaction with imidazole gives corresponding N-glucosides, and of course N-glucosides also could be alpha or beta. And just like O-glucosides, N-glucosides are also non-reducing sugars. An aldose contains, of course, an aldehyde group, which is oxidized preferentially to alcohol groups, numerous alcohol groups that a monosaccharide may contain. A monosaccharide, besides the mentioned aldehyde group, contains number of secondary alcohol functionalities and one primary alcohol group. Primary alcohol group is more reactive than a secondary and is oxidized preferentially to secondary alcohol groups. At the same time, the most reactive group towards oxidation is an aldehyde group, and you have seen that when we examined Tollens and Fehling tests. Products were actually corresponding aldonic acids, and you will see aldonic acids in a minute. But it is possible, by the action of specific enzymes, to oxidize primary alcohol group. In case of glucose, that would be alcohol group on carbon 6. So by the action of enzymes, it is of an enzyme, specific enzyme, it is possible to oxidize alcohol group on carbon 6, primary alcohol group, and leave aldehyde group intact. Product is corresponding uronic acid, and that uronic acid may exist in open chain form or in aqueous solution. It's more stable in cyclic form. So in this case, glucose gives corresponding glucuronic acid. Glucuronic acids are very important, physiologically very important compounds. They are present in both plants and animals, and one of their functions is to detoxify toxic hydroxyl-containing compounds. An example would be morphine, because morphine and similar toxic compounds are not very soluble in water. On the other hand, because of the presence of numerous hydroxyl groups, anything attached to glucose, any small molecule attached to glucose or other monosaccharide is going to be highly soluble in water. So in this example, morphine reacts with glucuronic acid to form new ester bond between hydroxyl group of morphine and newly formed carboxyl group of glucuronic acid, and that ester is highly soluble in water and easy to excrete. So in general, water-soluble glucuronides are compounds that are readily excreted in urine, so those would be form of toxic compound conjugated to glucose that is used to remove them from the organism. When monosaccharides are oxidized in Tollens or Fehling test, product is corresponding aldonic acid. So aldonic acid is a monosaccharide where aldehyde group has been oxidized to carboxyl group. We have already seen that Tollens and Fehling tests are non-specific because they will also isomerize ketoses such as fructose to glucose, and then in turn oxidation will give gluconic acid. So we have a specific reagent to prepare aldonic acids that will only react with aldoses but not with ketoses, and that's bromine water, dilute solution of bromine in water. So actually dilute solution of bromine in water can be used to distinguish an aldose from a ketose, and that reaction is shown here. So glucose gives positive reaction with bromine water because it's oxidized to gluconic acid, while fructose will give negative reaction. So this is the method to distinguish aldose from a ketose. And product in general is an aldonic acid. On the other hand, oxidation with stronger oxidizing agents, such as nitric acid, oxidizes both the aldehyde functionality and the primary alcohol functionality. And then product is corresponding aldaric acid. In this case, glucose is oxidized to glucaric acid. So in this case, we have two carboxyl groups. Both aldehyde function and primary alcohol function have been oxidized to carboxyl groups. So product is a dicarboxylic acid. And in this case, even though starting material was chiral, resulting aldaric acid, so those are aldaric acids, resulting aldaric acid may be achiral, that means not chiral. Achiral means non-chiral. That's the case if molecule is symmetric. For example, something like allose. So oxidation of allose gives symmetric molecule, mesoisomer, and then the product is not chiral. Another example is galactose. Oxidation of galactose also gives a mesoisomer compound that has planar symmetry going through the middle of the molecule, and it's not chiral. Besides oxidations of carbohydrates, another important reaction of them is reduction, in particular reduction of monosaccharides. Products of reduction of monosaccharides are polyalcohols. All of the functional groups are hydroxyl groups, alcohol groups, and such alcohols are called alditols. One really good, convenient reagent is sodium borohydride. It's readily available, easy to handle, and so the sodium borohydride reduction of aldehydes gives a corresponding alditol. Note that in case of a ketose, it's shown here on example of fructose, the corresponding alditol actually has new chirality center. So carbon 2 of fructose is carbonyl carbon. Upon reduction, it becomes new chirality center. It's shown here in red. Since reduction is more or less random, so new hydrogen, hydride anion comes from either side of the carbonyl group with more or less equal probability, we obtain a mixture of two alditols. In this case, mixture is glycitol and mannitol. And as was the case with aldaric acid, even though starting monosaccharide was chiral, resulting alditol may be achiral if it is a mesoisomer. And as shown before, allose and galactose give non-chiral products. In addition, reactions of different monosaccharides may produce the same alditol. So, for example, reduction of glucose or glucose will produce the same alditol, glycitol. We know it is the same because new product in Fischer projection is the same in both cases. Remember from organic chemistry course that Fischer projection can be rotated by 180 degrees and it still gives the same compound. So it still represents the same compound. So glycitol obtained by reduction of glucose is the same one as obtained by glucose. The only difference is that formula is rotated by 180 degrees. So keep that in mind, that different monosaccharides could give upon reduction or for that matter sometimes oxidation the same product. Some alditols are actually found in nature. D-glucitol is called sorbitol and is found in various fruits and it's used as a sugar substitute. D-mannitol is found in mushrooms, olives and onions. And semi-synthetic D-xylitol, shown here, is used as sweetening reagent. These sweetening reagents are not considered to be the best, not the healthiest. They may be causing some digestive problems. And this completes our review of reactions of monosaccharides.